Welcome. We are talking about carbohydrates today, introducing that topic. If you join me on page 159, you're going to notice that this day we are talking specifically about glucose and other monosaccharides in this video. The next video, which is the other video for our carbohydrates topic, we'll be talking about disaccharides and polysaccharides. What we'll be doing in this video is learning how to classify monosaccharides according to their functional group and number of carbons, and also learning about a couple of reactions of monosaccharides. Before we begin, I'd like us to zoom in a little bit. I'd like us to start by thinking of a big picture overview. I'm going to say if we're talking about all carbohydrates that there are, you've heard of sugars, for example, starch, for example. How do all those relate? All carbohydrates can be classified into one of three categories. And the three categories are monosaccharides, disaccharides, and polysaccharides. In this video, we'll be talking about monosaccharides. In the second video, we'll be talking about di and polysaccharides. So what is a monosaccharide? Glucose is an example of a monosaccharide. If you look at the structure here of glucose, first thing you notice, at least I hope, is that there's 6 carbons. 1, 2, 3, 4, 5, 6. So the prefix mono for monosaccharides is not talking about how many carbons there are, because glucose is a monosaccharide and glucose has 6 carbons. We'll see when we flip the paper over a number of examples of monosaccharides, but I'm going to list 3 right now, the 3 most common monosaccharides that we'll be discussing. Glucose is the first. Glucose is sometimes referred to as blood sugar. It's the sugar that's found in your blood when you get your blood sugars measured, if you do. It's sometimes referred to, its older name is dextrose. In the medical field, to this day still, if you get an IV bag with glucose, it usually is labeled as dextrose. Those are the same. So that's the first monosaccharide to identify. The second is fructose. That's fruit sugar, the sugar found in many fruits. And the last one is galactose. Galactose is not one that you've heard of, but we'll see in the next video when we learn about disaccharides why we want to highlight galactose as a monosaccharide. I will list common disaccharides and polysaccharides, and we'll be returning to those in the second video. The most common disaccharide is sucrose. That's the sugar that is often added to food. It's added to pop and baking and so on. Lactose, it's the sugar found in some dairy products, and maltose. So we'll be learning about those in the next video. And then polysaccharides, starch. That's the carbohydrate that's found in bread and potatoes and rice and pasta and so on. Glycogen, which is how our bodies store carbohydrate, and cellulose, which is how plants, the cellulose is in plants. So we'll talk about these in the second video. I just want to highlight them here to start, to give a big picture overview. Again, what we're planning to do in this video is identify monosaccharides and learn how to classify them based on functional group and carbons found in that structure. And then we'll look at a few reactions of monosaccharides, but not this one. We are not looking at reduction. Given our shorter semester, because the move going online and so on, we're crossing this out. So we're not ever going to be talking about reduction of monosaccharides in this course, this semester, spring 2020. It doesn't happen for the most part in your body, so this is why we're crossing that out. This one is a really, really important one though, so we're focusing on this. We'll also see this. So please join me in turning the paper over to page 160. The caption on the top of this table is monosaccharides classifying structures. Sure enough, let me zoom out just a little bit. Sure enough, all the structures on this page are monosaccharides. So everything on this page is a monosaccharide. It will be easier for you to identify that once we identify disaccharides. Then it'll be more apparent to you how to notice that these are all monosaccharides. But for now, I'm telling you these are all monosaccharides, but there's a couple of key differences among them. First of all, you see there's a bunch, right? What is this, probably 12 or 15, I don't know, 16, 18? There's a bunch of different structures, and each of these structures is a different monosaccharide. Glucose, mannose, glucose, idose, galactose, tallose, and so on. Here's ribulose, here's fructose down here. These are different monosaccharides. On the previous page, I highlighted by name 3 that are kind of important in our discussions: fructose, galactose, and glucose. You don't have to be able to identify those by structure, but what you do want to be able to do, we'll practice this now, is identifying each of these as what kind of monosaccharide. So let me tell you what I mean by that. If you look, I'm going to draw a dashed line right in the middle of this page. Because if you look on the top half of that dashed line, all of these structures, and notice that they've been grouped together already. They're kind of connected almost like a family tree. This group of structures, they all have one thing in common that's different from the structures on the bottom. And I'm going to highlight for you what that one thing in common is. CHO, as you know, is an abbreviation for aldehyde. That is the abbreviation for the aldehyde functional group. Here's the unabbreviated look at that functional group. And as you know, that's aldehyde. Every structure on this top half has that same functional group. CHO, CHO, that's aldehyde, 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 and aldehyde, and so on. What else do you notice? Why don't you pause your video for a moment and look at the structures. What other functional groups do you notice? Thank you for doing that, because now I can summarize what you just did. You will notice that all the monosaccharides all have between 3 and 6 carbons. The small ones have just 3 carbons, the larger ones have 6. Actually, every carbon has a functional group attached. And what you just noticed when you took a look, usually that functional group is alcohol, but also there is always what I'll call the special. There's always one special functional group. And all that I mean by that, special functional group will either be aldehyde or ketone. It's never both. It's either aldehyde or ketone. And that's what we just saw in those structures on the top half, right? There are 3 to 6 carbons. Yep. Every carbon has a functional group. And as I asked you to do a moment ago, what are those functional groups? Let's look at arabinose, for example. This carbon has OH, that's alcohol. OH, alcohol. OH, alcohol. OH, alcohol, and then aldehyde. So every carbon has a functional group. Usually that functional group is alcohol, but in addition to all of the alcohols, there's always one special functional group. The special functional group, and I put that in quotes because that's not official, I'm just calling it that. The special functional group is either aldehyde or ketone. For all the structures on the top half of this page, all of them have aldehyde as their special functional group. We pointed those out a moment ago: aldehyde, 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 and so on. The last little bullet that I'll put here to identify monosaccharides is this: the names end in ose. So they do not follow an IUPAC naming pattern. So everything you've learned with aldehyde, ketone, and so on does not, the IUPAC system does not apply, but you'll be able to notice that their names end in ose. So these here are monosaccharides. They will end in ose. And because they have aldehyde as their functional group, these are all referred to as aldoses. All of these are classified as aldoses. Glucose is in aldose because it has aldehyde. Xylose is in aldose, ose because it's the sugar, and ald because aldehyde. If you look on the bottom half of the page, you will see that there's not aldehyde. Pause your video, notice that there's not video, and then tell me what the special functional group is. So pause your video and I'll wait. Okay, thank you for doing that. What I want you to notice in all of these, I'll pick this for example, here is a ketone, here is a ketone, here is a ketone. Each of these all have ketone, not aldehyde. Remember, ketone looks like this. These all have ketone, not aldehyde, so they are all these are classified as ketoses. Ose because it's sugar, ket because it has the ketone functional group. So when we're classifying monosaccharides, they will either be classified as ketose or aldose. It's always one or the other, always ketone or always aldehyde. It's one or the other. What's with the classifications on the far left, these hexose, pentose, and so on? These monosaccharides here are classified as pentose. These are classified as hexose, and so on. I think you can speculate on what that means. Pent means 5, so pentoses have 5 carbons. Hexoses have 6 carbons. Tetros, that's a new, this is the first time we've seen TETR as a prefix for 4. That's not common. It's coming up here with monosaccharides. Same with tri. That's true and that's true, but I will tell you that most of the sugars that we encounter in our body chemistry have 5 or 6 carbons. So pentoses and hexoses are more common. In fact, you can see that there's only 2 examples of tetroses up here, but there are 8 examples of hexoses down here. So again, hexoses have 6 carbons, pentoses have 5, tetroses have 4, trioses have 3, and you can combine those 2 types of classifying, number of carbons and functional group. You can combine those to identify a sugar based on both. I'll flip the paper over and remind you that was our goal. Classify monosaccharides according to functional group and number of carbons. So aldose or ketose, hexose, pentose, etc. Glucose, for example, I noticed that it has 6 carbons, 1, 2, 3, 4, 5, 6, and then I check to find out if its special functional group is either aldehyde or ketone. It will be one or the other. It's aldehyde. And since it's 6 carbons with aldehyde, that would be classified as aldohexose. Aldo for aldehyde, hexose for 6 carbons. If I flip the paper over to do a couple of more examples with you, let's take a look at fructose. Fructose has 6 carbons. Its special functional group is a ketone. And so it would be classified as a ketohexose. Ribulose, either of these that I'm pointing at here, they each have 5 carbons with ketone. So those would be called ketopentose. How about ribose? How would you classify ribose? I would say that it has 5 carbons, aldehyde, so it would be an aldopentose. So again, the first part, aldo or keto, tells you if there's aldehyde or ketone present. The pent or hex or tri would tell you how many carbons total. And then the ose is an indication that it's a sugar. So what we've just done is we've learned how to classify monosaccharides according to functional group and number of carbons. I'd like you to practice a few more so that you feel like you're solid, but beyond that, it's fairly straightforward. The rest of the video will be looking at oxidation of monosaccharides. Condensation, of course, we will look at. We will see it in both carbohydrate videos. But right now I want to emphasize the oxidation of monosaccharides. So we will go to the next page, page 161, if you can join me there. I've listed a monosaccharide here. And again, you don't probably fully understand how do I know that that's a monosaccharide. It has 3, 4, 5, or 6 carbons, a bunch of alcohols, and then either aldehyde or ketone. That's hopefully you notice that. But as I said, once we introduce disaccharides, I think it'll be easier for you to identify this as a monosaccharide. So we want to look at the reaction, and specifically we want to look at oxidation. You already know, remind yourself that oxidation, it's not different from what you've already learned. Oxidation means gain bonds to O. And with monosaccharides, it will be typically a weak oxidizing agent. A weak oxidizing agent such as toluenes or benedicts. That's what we'll be looking at first, and that's what you've seen in the lab. And remember, with a weak oxidizing agent, alcohols do not react. Alcohols do not react. So what would happen if we try to do oxidation of this? And I'll remind you it's weak. So the alcohol will not get oxidized, but what about aldehyde? How do we do this? How do we complete this reaction? This very same way you've been doing it, copy that structure over, nothing changing except leave the hydrogens invisible. So copy everything but leave the hydrogens invisible. 1, 2, 3, 4, 5, 6. There are 6 carbons. Remember, the intersection means carbon. I am drawing that carbon in there just to help us see it better. There. So I've just copied this structure over with no hydrogen showing, just the C's and the O's. And then you ask yourself, is there room on carbon for more bonds to O? I see there's a ton of carbons with bonds to O already, but remember, alcohols do not react with benedicts. So this will not react, this will not react, or this, or this, or this. These bottom carbons will not react, not get oxidized with a weak agent. Only this top one can, because it's not alcohol. And you ask yourself, is there room on this carbon right here for more bonds to oxygen? Right now there's 1, 2, 3 bonds showing. So yes, there is room for one more. That would look like this. Is there room for any more bonds? Let me zoom in a bit. Is there room for more bonds on that carbon? There's not. This is a double bond, so 1, 2, 3, 4. So this is our final answer. To fill in the functional groups again, we could go back in and add all the H's. But what I want you to notice now is this is not a monosaccharide anymore, because the aldehyde has been converted, and you know what it's converted to. It's converted to a carboxylic acid. That's true, but really the key thing I want you to notice is it's not a monosaccharide anymore. What we just saw is that aldoses can get oxidized. All aldoses, if there's an aldehyde, they can get oxidized in the way that we just showed. Let me have you practice that. I'm going to have you pause your video. This is the same thing we just did, but cover up that top part and see if you can complete this reaction. you're going to try to oxidize this sugar here. So pause your video, cover up that top, and practice it on your own. When you do that, this is what you see. In fact, I could draw it the same way they did there if we want to. We'll get this structure, which again is not a monosaccharide anymore. The monosaccharide has been oxidized. For reasons that we're not getting into in detail in this course, but we'll see a bit of the reason why in the next video, it's also true that ketoses can get oxidized. And you might say to yourself, huh? I thought ketones cannot get oxidized. That's correct. So first, the aldose to ketose rearranges its structure. So this is the reason. You don't need to know the reason, but if you're curious, this is the reason. What you do need to know is that aldoses can get oxidized and ketoses can get oxidized. And what that means is this: all monosaccharides can get oxidized. We just saw that monosaccharides are either aldoses or ketoses. They both can get oxidized, which means all monosaccharides can get oxidized. And what that also means is that all monosaccharides are reducing sugars. That's a term that biochemists use and we will be using. A reducing sugar is just defined this way: a sugar that can get oxidized. Since monosaccharides can get oxidized, monosaccharides are reducing sugars, because a reducing sugar is a sugar that can get oxidized. And what you've seen in the lab is can get oxidized would mean a positive Benedict's test. That's how you would measure that in the lab. So all monosaccharides will give a positive Benedict test. All monosaccharides are reducing sugars. That means they will give a positive Benedict test. So that's enough for this video. In the next video, what we'll be looking at is this bottom reaction. It's beginning to help us see how monosaccharides combine to form a disaccharide. And here's a sneak preview. It's going to start by forming a ring. I indicated that a little bit up here. We'll be looking at that more in the next video. So join us for the next video after this one. Thank you.